Okay, let's go ahead and get started. So today I'm going to continue with our discussion of the general theory of relativity. And I'll present to you a basic discussion, very qualitative discussion, of the structure of general relativity and the basic ideas before moving on to present a fundamental concept known as the equivalence principle, which is really the basic observation and fact about nature which underlies Einstein's formulation of the theory of gravity as a statement about the geometry of space-time. So let me remind you of where we left off last class. So in Newtonian gravity, the theory consists really of two related but distinct statements. The first is that there is a gravitational potential phi, which is determined by solving some equation of motion. But, for example, if you have a particle or an object with mass big M, and that object is spherically symmetric, then the gravitational potential is Newton's constant times the mass of the object divided by r, the distance to the center of the object. And the second component of Newton's theory of gravity is an equation which tells you how objects move in the presence of some gravitational potential. And in particular, the equation is Newton's law, which says that the force on an object due to gravity is minus the mass of that object times the gradient of the gravitational potential, which is then equal to the mass times the acceleration of the object. Here, little m is the mass of the object whose motion we're studying, and big M is the mass of the object which creates some gravitational potential. If we were studying the orbits of the planets, for example, big M would be the mass of the sun, r would be the distance from some planet to the sun, and little m would be the mass of one of those planets. And of course, the simplest application of these laws is the case where phi is equal to 0, so that there's no gravitational potential, in which case Newton's law just says that the acceleration is constant and objects will move on straight lines. In general relativity, our point of view has changed somewhat. And what we say is that gravity is due not to a gravitational potential, it's not due to some sort of field like the electric field or the magnetic field or the gravitational field, but rather to a property of space-time itself. And in particular, it's due to the curvature of space-time. And the basic dynamic object that you study in general relativity is a metric which is the quantity that tells us how it is that space-time curves. Now, this is not a class on differential geometry, so I won't delve too deeply into the mathematics of what the metric is, but we will, by the end of next class, learn what the metric is and what it's good for and how it will tell us, for example, how to modify Newton's law in this new way of thinking about space and time. So, before delving into any of these details, however, let me just tell you what the concepts are in general relativity that replace these two basic concepts in Newtonian gravity. The statement that there's a gravitational potential due to the presence of matter, and then Newton's law tells us how objects move in the presence of a gravitational potential. So in general relativity, the statement that the presence of mass creates a gravitational potential is replaced by a statement that the presence of matter, and in particular the presence of mass or energy, makes space-time curve. I remind you that, of course, in special relativity, the distinction between mass and energy is somewhat ambiguous. There's no real notion of mass separate from energy. So, in particular, what that implies is that not only should normal matter, like the Earth or the Sun, make space-time curve, but also, for example, light, something which is massless, but also has energy, can make space-time curve. And the equation which determines the curvature of space-time due to the presence of matter is known as Einstein's equation. And it's the general relativity version of the statement that the Laplacian of the gravitational potential is proportional to the matter density, which was the basic equation of Newtonian gravity that we encountered last class. I'm not going to write down Einstein's equation for you. I could, it's easy enough to write down, but you wouldn't understand any of the symbols that I used to write it down, so it probably wouldn't be a very productive use of our time. So instead, let me give you a simple example of this rule at work. So, for example, in the absence of mass and energy, space-time is flat Minkowski space. So in particular, in the absence of mass and energy, space-time should have no curvature. The word that we use to describe a geometry with no curvature is we say that it is flat. And in particular, space-time is the usual space-time that we have been using so far in this course. Namely, it's the usual space-time that we use in the study of special relativity in the absence of gravity. The second rule, or the second principle that makes up Einstein's theory of general relativity, is a rule for determining how objects travel through curved space-time. So, again, I could write down the equation for you. It's not that complicated. And if we wanted to spend some time going through the mathematics of differential geometry, you could surely understand that equation quite precisely. But instead, this is actually a rule that I can state to you in a completely intuitive way without any equations whatsoever, and it should hopefully make perfect sense to you. So let me explain this rule to you. And this will be the analog of Newton's third law, F equals ma, in curved spacetime, that is to say in general relativity. So let's remember that without gravity, spacetime is flat and objects move in straight lines. That's, among other things, a consequence of Newton's law. Objects in motion tend to remain in motion at constant velocity unless acted on by some external force. So the picture that I want you to have in your head, then, is that space-time is some sort of flat plane, which I've tried to draw here. And if you wish to understand the trajectory that an object takes between 2 points, it's the straight line between those 2 points. And in particular, it's the line that minimizes the distance between 2 points. The shortest distance between 2 points is a straight line, at least if you're on a flat piece of paper. The rule in general relativity, however, is that in curved spacetime, objects will move on what are known as geodesics. What is a geodesic? A geodesic is a curve which is as straight as possible given the curvature of spacetime. Now, what do I mean precisely by as straight as possible? Well, there are two completely equivalent ways of understanding what I mean by a curve which is as straight as possible. So one way is that I could say that it is a curve which minimizes the distance between 2 points, just as in flat space, we would say that the shortest distance between 2 points is given by a line. On some curved space, the definition of a geodesic is it is that curve which minimizes the distance between 2 points, given the fact that your space is curved. So, for example, let's say that I have a curved geometry, which is a sphere. That's a slightly lopsided sphere, but that's okay. And let's say that I want to get between 2 points that are on the equator of the sphere. Then you don't travel on a straight line between those 2 points, at least if you're staying on the surface of the sphere. Instead, what you do is you travel along an arc of a great circle. So on a sphere, the geodesics are great circles. Put it another way, if you want to travel their line on the equator of the Earth, the way that the shortest distance between 2 points is following the line of constant latitude, longitude. I never quite remember which one it is. It's the one where you stay on the equator to get between those 2 points. Whereas likewise, if you want to get between Montreal and London, say, you don't stay on a curve of constant latitude or longitude or whatever it is. The shortest distance is found by flying over Greenland or something like that, where you minimize the distance by going along the arc of a great circle. That takes you somewhat north of the trajectory, the constant line of constant latitude or longitude between Montreal and London. Another way of thinking about a geodesic is that it is the curve that an ant would take. What do I mean by that? If you were an ant crawling, say, on the surface of a balloon, or a person crawling on the surface of the Earth, then you wouldn't really perceive the curvature of the balloon, at least if the balloon is inflated and much bigger than the ant. You would just travel along a line that looks straight enough to you. So the same way that if I wanted to walk between this room and the other side of the room, I would walk on what appears to me to be a straight line, but actually, due to the curvature of the Earth, would be slightly different from straight. And the way that the motion of objects is determined in general relativity is simply the statement that in the absence of any force but gravity, so in the presence of gravity but no other forces, objects travel on geodesics. So this is a rather beautiful way of thinking about things. So remember, the basic statement of Newtonian gravity is that in the absence of gravity, objects travel on straight lines. In general relativity, we now generalize that statement to say that in the presence of gravity, objects travel on quote-unquote straight lines. They don't travel on straight lines, they travel on quote-unquote straight lines, where a quote-unquote straight line is the line that an ant thinks is a straight line. It's the one which is as straight as possible, given that space-time is curved. Are there any questions on this? Yes.
So are orbits geodesics?
Yes. But they're geodesics, so of course, if you study the motion of the Earth around the sun, and you think of the solar system as being a flat plane, okay, then obviously Earth goes on a circle. It doesn't go on a straight line between those 2 points. So it's not a geodesic through that flat plane. It's a geodesic through the curved geometry that describes space-time in our solar system. Excellent question. Good. Yes?
So if the planes are geodesic, they're not accelerating, they're going straight.
Yes. So that's exactly right. That's exactly right. So that is the basic observation that really leads to which I'm now going to describe, which is known as the equivalence principle. That's exactly correct. So the statement, just to reiterate, is that if you move along one of these geodesics, you're not subject to any acceleration. Or at least yes. Well, yeah. In the sense that we could make a little bit more precise if we went into the mathematics of general relativity in more detail. Yes, there's a question.
When you say that geodesic is the curve which minimizes distance, do you mean only spatial distance or space-time?
No, of course, what I mean is that in GR, by distance, i.e. the distance that is minimized by a geodesic, we don't mean distance, because we've learned that distance doesn't mean anything in special relativity. We mean invariant interval. And as we will see later on, either this class or next class, it is precisely the form of the invariant interval that gets modified in general relativity to reflect the fact that space-time is curved. So the basic dynamical variable that we use to describe the curvature of space-time is a variable which tells us how the invariant interval differs from what we thought it was in our previous discussions of special relativity. Questions? Yeah.
Is the distance sometimes not minimized, but like a saddle point, like extremized?
It could be, yes. I should say extremized. Okay. So, yeah, I should say extremized, but I didn't say extremized because extremized is more complicated sounding than minimized. I mean, for the picture that, visualizing a curved four-dimensional space-time is very difficult in your head, okay? You can break your brain if you try and visualize it. So what I want you to keep in your head is this picture of the sphere where it's a nice space, there's no time, it's just space, and you have some curvature, and you're minimizing the distance. But the actual statement in general relativity is that you extremize not a distance, but an invariant interval. And just as on a sphere, the curvature of the sphere modifies how you measure distances on the sphere from our usual Euclidean geometry notions, in general relativity, the presence of a metric modifies what we thought was the formula for the invariant interval. So, for example, the statement that a sphere has curved geometry means that if you were to try and draw a triangle on the sphere, and the definition of a triangle is that it's something connected by three straight lines, where straight lines mean quote-unquote straight lines to these geodesics, you would see, for example, that the sum of the angles on the triangle is not equal to 180 degrees. So that's an example of how the geometry, the curved geometry of a sphere is different from that of a plane. Just as an aside, can anyone tell me what the sum is? Is the sum going to be bigger or less than 180 degrees? Okay, good. Yeah. The easiest way to see that is to imagine 3 points, 2 of which are on the equator and 1 of which are on the North Pole. Okay, and then you could you can see that the two angles between connecting the equator and the North Pole are going to be 90 degrees, and so you can have anything bigger than 180 degrees because of the angle between the 2 points of the sphere at the North Pole. Maybe, I'm not sure if that was clear, but think about it. Draw the triangle on a globe where you connect 2 points on the equator with the North Pole. You'll see that they have to sum up to bigger than 180 degrees. Incidentally, as a historical aside, the idea that the structure of space that we live in might be curved actually goes back quite a long way. So, for example, Gauss, this famous mathematician, performed actually the following very interesting experiment. Okay, so he took a couple of graduate students. Graduate students are expendable. He took 3 graduate students, and he sent them to the top of 3 tall mountaintops. And he said, light a big fire on top of the mountaintop and measure the angle between the 2 other fires that you see. And he asked whether a triangle that's very, very big actually has angles that add up to 180 degrees. Okay? And if he really had the right idea, because, in fact, due to the curvature of the geometry of space-time, because of the Earth's mass, in fact, the sum of the angles on that triangle is not 180 degrees. But it was far, far too small an effect for him to measure. And by the end of this set of lectures, you'll be able to estimate. In fact, you could do it right now if you're bored. Use dimensional analysis to estimate how different those angles are from 180 degrees due to the curvature of the geometry of space-time and general relativity. You have every single piece of information that you need to answer that using dimensional analysis. I wish I hadn't said that. Otherwise, I would have put it on the midterm next week. Okay. Anyway, excellent practice problem for the midterm. Okay. Good. Why, then, is it possible to formulate general relativity in terms of the geometry of space-time? So why does gravity have a geometric interpretation? And the answer is something known as the equivalence principle. So, the basic observation of the equivalence principle is the following. And in fact, it's something that we can understand just as a statement about Newtonian gravity. So, recall that in Newtonian gravity, the gravitational force on an object is minus the mass of the object times the gradient of the gravitational potential. And Newton's law says that the motion of the object is determined by setting F equals to ma where A is the acceleration vector of the object. And the truly remarkable thing about these two equations, and something which I think is so remarkable that we don't even notice it, is that there is a parameter m that's appearing in equation 1, and also a parameter m appearing in equation 2. And they just happen to be the same. So, in principle, the mass m appearing in the first equation, which we could call m sub g for gravitational mass, could not be equal to the mass that we call m sub I for inertial mass, which appears in the second equation. So m sub g is the parameter m appearing in the first equation. M sub I is the parameter appearing in the second equation. The first equation is a statement about how an object feels, about the gravitational force on an object. And the second equation is a statement about how an object moves in response to a force. And it just happens to be that for all known objects, those two parameters just happen to be equal. And so we just use one symbol for it, m, neglecting the subscript. And what this means is that the equation which determines the motion of an object is found by setting those two forces equal to one another. So what is the equation? It says that A is minus the gradient of the gravitational potential is independent of the mass of the object that we are studying. The m's on the left and the right-hand side of that equation have canceled. Question?
I'm just wondering, for the equivalence of the inertial mass and gravitational mass, is this experimental data or?
This is an experimental fact about nature. Okay.
There's no.
It was first observed by Galileo. Okay. I mean, it may have been observed well before that, but it was first made a big deal of by Galileo, who went ahead and dropped all sorts of objects off of the Leaning Tower of Pisa, or at least that's the way the story goes, and saw that they all take exactly the same amount of time to hit the ground. Okay. A feather and a bowling ball fall in exactly the same way, except for pesky things like air and stuff like that. Okay. But you can go online and see a video of some astronaut on the moon dropping a feather and a bowling ball, and you'll see that, in fact, they do fall at exactly the same speed. I don't think it was a bowling ball. I think that at $100,000 per kilo, they didn't probably bother to bring a bowling ball to the moon, but it was probably something else. Okay. So what does this mean? This means that there is a special set of trajectories which all objects follow if they are subject only to a gravitational force. Namely, they're found by solving this equation that the second derivative of the position is the gradient minus the gradient of the gravitational potential. And this, indeed, is what it is that allows us to think of gravity in terms of geometry. Because you could imagine that you have some region of space, and you could study the set of trajectories that objects will move on in that space. And let's say that they're all straight lines, okay, in the usual sense. Well, then everything's good. That's exactly what we would expect for objects moving through a flat space. But let's say that there was a different set of trajectories, which I'll try and draw. I'm not a very good artist. But let's say that we studied the trajectories that an object took through space due to gravity, and they looked like that. Sorry, those aren't very good. Let me try and redraw these. Let's say that they looked curved in some way. Like that. Well, then there's two different ways you could think about these curved trajectories. You could say that these curved trajectories are not straight lines because you have a gravitational potential and you're solving the equation that the acceleration is the gradient of this gravitational potential. Or, and this was Einstein's insight, you could think about these curved trajectories as due to the fact that the trajectories are straight, but space itself is curved. For example, in this, so let me try and draw what space would look like for those curved trajectories that I've sketched. Space would have to have some sort of lump there, if you know what I mean. Is that clear? I just made it less clear. Space would have to have some sort of lump. And the reason why our trajectories are curved is that they're trying to avoid that lump in space. For example, if I experimentally tried to get between here and Vancouver along the straightest line, you would discover that according to the grid of straight lines that I would lay down here in Montreal, that you wouldn't be traveling on what we would perceive as a straight line. You would be traveling on what we would perceive as a curved line. And you could say, well, that curvature is due to some strange principle that we would have to develop some laws to try and understand. Or we could just observe that this means that the Earth is curved. Okay. So Einstein's observation is that exactly the same thing can be said about gravity. And the reason why it can be said is that every object, no matter what its mass is, travels on the same trajectory. This would not work if, for example, a bowling ball and a ping pong ball fell differently. Because then there would be two different sorts of trajectories. And we couldn't attribute it to some property of space itself. We would have to attribute it to some special way that gravity interacts with a bowling ball as opposed to a ping pong. Yes?
How can their trajectory be mass independent if their mass is also curving space-time?
Okay, good. So that's a good point. Okay. So the statement that in Newton's law, okay, we have the statement that the acceleration is independent of the mass of the object. But what we're really doing is we're thinking of an example where the mass of the object is sufficiently small that we don't have to worry about it creating its own gravitational field. Okay. In the example of the solar system, the mass of the sun is vastly bigger than the mass of the other planets. Okay. So in the solar system example, we could study the motion of the Earth through the solar system by pretending that the Earth's mass is so small that it doesn't create any gravitational field itself. It's just moving in the presence of the sun's gravitational field. It's just moving in the potential created by the sun. Now, of course, if you want to study the moon, well, you'll get the wrong answer if you throw away the Earth's gravitational field. There, you have to take into account the Earth's gravitational field, and in fact, it's the biggest contribution to the motion of the moon. Okay. So it's important to understand that when I say that I have objects moving on a particular trajectory through a fixed space, then we have to take into account the fact that, and that's really only strictly speaking true in the limit where I neglect the mass of the object that I'm studying, at least as far as its as how it makes space-time curve itself. I mean, once you start taking that into account, general relativity gets more complicated because you then have to, I mean, in some way, one of the reasons why general relativity is a more difficult subject than Newtonian gravity is that the equations take all of those things into account simultaneously. Okay. Mass. So a mass will make space-time curve, but the curvature. But okay, here's an example that'll really get you confused. So energy makes space-time curve as well, and the curvature of space-time is a gravitational field. Gravitational fields have energy because everything has energy. Okay. So that means that the curvature of space-time makes space-time curve. Okay. And so what that means mathematically is that the equations of general relativity are nonlinear, so they're very difficult to solve for that reason. So you're right, and all of these thoughts have to be folded in to the full mathematical description of the theory. Yeah.
When we say something is curved, we mean it's curved like relative to some other space. So in any sense that we have the absolute flat space.
Yes. Okay. That's an excellent question. When we say curved, we mean curved relative to what? Okay. There are a lot of. So what do I mean by a flat space? What I mean by a flat space can be described in any number of ways. Okay. In the context of usual Euclidean geometry, a flat space is one where the postulates of Euclid are correct. So the sum of the angles in a triangle is 180 degrees. Two parallel lines will never meet. And both of those postulates will be wrong in a curved geometry. Parallel lines on a sphere meet. For example, the lines of constant latitude or longitude, whichever it is, meet at the north and south pole. The sum of the angles in a triangle is not 180 degrees. So these are universal notions, just given the notion of what it means to have a straight line, of how we can decide what we mean by a flat space. In the context of general relativity, what we mean by a flat space is that the invariant interval is given by the formula in special relativity that we worked out earlier in this course. Okay. So in general relativity, that's even worth writing down. What do we mean by a flat space? A flat space is one whose invariant interval is given by the usual formula that the invariant interval between two events is the difference between the distance between the two events and their time separation as measured in some coordinate system, as we learned in special relativity. So in normal spatial geometry, a flat space is a Euclidean space, namely one where the postulates of Euclid apply. And in general relativity, a flat space is Minkowski space, one where the postulates of special relativity apply. Good. Other questions? Yes.
So in GR, then, like in geometry, it's an never applicable.
Sorry. What's that?
In GR,
Euclidean.
Yeah. Geometry.
Sorry.
It's just completely not applicable.
There are cases where Euclidean geometry is applicable. So, for example, in general relativity, there are examples of space-times where the spatial geometry, the geometry of space, is completely flat in the sense of Euclid, but where the behavior of the time direction is somewhat different. Okay. An example of such a space-time would be our universe, because to a great degree of accuracy, in fact, quite somewhat surprisingly, it was observed over the last 20 years or so, our geometry, as far as we can tell, is completely spatially flat, okay, even on cosmological scales. Okay. But our universe is still expanding, okay, so there's still a curvature of space-time, even though the curvature of the spatial part of the geometry is completely flat. Other questions? Okay. Yes?
It's completely flat. Isn't there still some points where, for example, planets make bumps?
Oh, sorry. But yeah, no, you're right, of course. By completely flat, I mean flat when you average over very long distance scales. Of course, in our solar system, space-time is not nearly flat at all. But I was thinking of cosmology, where we're talking about the structure of the universe on very large scales. And given that space is curved on very small scales, by small I mean the solar system or the galaxy or something, you might think that, well, there's no reason for space to be approximately flat on very large scales. Okay. But it turns out, and this was a very surprising observation, that space-time is flat in that spatial sense at very large scales. Okay. In that a parallel line that you drawn between, a pair of parallel lines drawn on cosmological scales don't intersect. Okay. We'll spend some time on cosmology after this discussion of GR. Yes?
So is the curvature of space-time something that all observers agree on?
Excellent question. That's an excellent question. There are notions of curvature that everyone can agree on, and notions that are observer dependent. Okay. Just as the energy and momentum of an object are observer dependent considered individually, there are quantities that are combinations of energy and momentum that all observers agree on. And so there are components of the curvature that are observer dependent and components that are not. Okay. So a statement like, if I draw a triangle, so one way of measuring the curvature of space at a point would be to draw a triangle and look at the sum of the angles of the triangle. That's something that we could all agree on. Okay. But there are other notions, a little more complicated, that are observer dependent. Question? Yes?
Do they average out between observers?
Do they average out? Well,
I mean, if you have quantities that vary for one observer and others that vary for the other, is there some invariant?
There are invariant notions of curvature. So, for example, the sum of the angles in a triangle is some invariant notion of curvature. But there are other notions of curvature that are observer dependent. We could go through it if you want. But I'd rather not do that. I don't know. I don't want to turn this into a course on differential geometry. There's nothing that you guys in principle couldn't learn, but last year when I taught this class, I spent like 3 weeks on general relativity, and I think I went beyond what was appropriate. So I think I want to keep the mathematical stuff out of our discussion of GR. I think maybe I'll change my mind, but I think that's the best way to proceed. But you can ask me afterwards, and I'll draw you a picture of precisely what such a notion of curvature might be. Good questions. Okay. Or should I tell you? Because it's pretty cool. Okay, I'll tell you. Okay. What would be an example of an observer-dependent notion of curvature? Okay. So let's say that we have this triangle here. Okay. So, Gauss sent his 3 graduate students up onto the mountaintop to measure the sum of the angles of this triangle, which is an observer-independent quantity. But there are other more complicated quantities that one could consider. For example, I could say, take a gyroscope. And That gyroscope has a little vector, which tells you that this gyroscope is spinning. It has some angular momentum vector. And you could transport it around this triangle. Okay. And if space is flat, then that vector will come back to itself. The gyroscope will be pointing in the same direction that it was pointing to begin with. But if space is curved, the gyroscope won't be pointing in the same direction. If you want to see an example of why that's true, let's consider a sphere. Okay. And then let's consider the following triangle. Let's consider the triangle that connects 2 points on the equator to the North Pole. Okay. And then let's start with a gyroscope. So this is the North Pole. That's where Santa lives. And then let's start with the gyroscope, which is pointing due north. Okay. Here, on the equator, on the point on the left. So then, as you transport this gyroscope pointing north towards the North Pole, your gyroscope will continue pointing north. It will end up pointing somewhere like that. Okay. And then, let's say that the 2 points on the equator had a separation of 90 degrees. Then that means that the relative angle between the gyroscope and this trajectory is 90 degrees, so that you could then transport this guy back down to the equator, and he'll be pointing due east, I suppose. That's east, right? Due east, and then you take that gyroscope back along the equator, and it's transporting due east. And so you see, for example, that this gyroscope will have changed by an angle which is equal to the either latitude or longitude, I never remember which, between these 2 points, so that's some angle theta, which will be the angle that your gyroscope will have precessed by as you take it to the North Pole and back down to the equator along this trajectory. And this is a quantity that depends on which direction the gyroscope was pointing in. And so in that sense, it is a more complicated notion than the simple number which parameterized the sum of the angles of the triangle. It was a notion that depended on a vector. Okay? And the vector, and so vectors, as we have learned, are things that transform under rotations. They're things that transform under Lorentz boosts, and so they're observer dependent. So things like this are things which are notions of curvature that are just as real as anything else. But you just have to take into account the fact that they transform in some way. I should say that it's not an accident that I use this example of a gyroscope, because this is, in fact, an effect which has been measured in general relativity, sort of most accurately by a recent experiment known as Gravity Probe B. And what they did, they built a very, very accurate gyroscope. They put it into orbit so that it was free as much as possible from the pull of the Earth's gravity, and it could travel on a geodesic. Okay, what is a geodesic? It's an orbit around the Earth, of course. And they measured the amount of precession of this gyroscope. And they verified all sorts of interesting features of general relativity. So, for example, the curvature analog of the sum of the angles being 180 degrees is very easy to verify experimentally. For example, every time you use your GPS and you get an answer that is within a kilometer of where you expect it to be, of where it should be, your GPS has corrected for that version of the curvature of spacetime. Okay, but the curvature of spacetime that is observer dependent, for example, the precession of these gyroscopes is much more difficult to measure, and it was only through this very sophisticated experiment that they were able to measure it. Okay, fact, it's sort of controversial because the experiment didn't do nearly as much as they said it was going to. So not everyone is a fan of that experiment. Yes, question?
And was it the experiment where they had them scramble the data?
Yeah. I mean, basically what happened, we don't need to go into too much of the details, but how do you build a gyroscope? Well, you need to have something that spins. Okay, and so they built these incredibly symmetric spheres, the most symmetric objects on the Earth. I actually had a friend in grad school who worked on this experiment, and he had one of the fifth most perfect sphere in the world as a paperweight. Okay, because the first 4 were sitting in a laboratory somewhere, but this one wasn't quite good enough, so he used as a paperweight. It's the worst possible paperweight in the world because it rolls around everywhere. The problem is that when you spin these things, they're made of some material. That material has charged particles in it. When you spin it, it creates a magnetic moment. Okay? The same way that if you took a sphere of charge, and you spun it, it would create current going around in a loop, so you'd get a magnetic field. And then when you study these gyroscopes, you need to have a very, very careful model of how these magnetic moments are within the material are interacting with one another. And so you need to know an incredible amount about the various forces on this material due to this magnetic fields. And one of the unfortunate or fortunate things about life is that gravitational forces are much, much weaker than electromagnetic forces. And so it turns out that in the actual experiment they didn't quite keep track of these things appropriately, so they had to get money from the king of Saudi Arabia in order to finish analyzing their data. Okay, so it's unclear. Basically, the upshot of the experiment is that they agreed with general relativity, but if they hadn't agreed with general relativity, people probably would have said that the experiment just was messed up, not that GR was wrong. Okay, but that's apropos of nothing. I will see you on Friday. Okay.